Hello and welcome to this virtual presentation. My name is Michael Heisel. Today I will be talking about how topography can increase the vertical transport of coarse and giant mineral dust in the atmosphere. My colleagues on this work are Biqing Chen, Jesper Kok, and Marcelo Chemecki at UCLA. This work is motivated by numerous observations of coarse mineral dust in the upper atmosphere. Commonly, dust is considered coarse if its diameter is greater than 5 micrometer and giant if it's greater than approximately 75. On the right is a volume distribution of dust in the Saharan air layer several kilometers above the Earth's surface. The dashed line is at 5 micrometers, such that everything to the right is coarse and giant, and you can see that a large portion of the dust volume in the Saharan air layer is in this coarse regime. However, if you turn to global models that deal with atmospheric dust, they either do not include coarse dust or severely underestimate its presence in the atmosphere. On the right is a comparison of models and observations for a series of different observation campaigns, where the blue lines representing the model ensembles are severely underestimating the measurements in a systematic way. This systematic underestimate indicates important mechanisms are missing from the models. One possibility is that small-scale topographic features enhance uplift of dust into the atmosphere, whereas most measurements in the near-surface region are in flatter terrains. This is a possibility pointed out in Rosenberg et al. JGR 2014, where their field measurements noted enhanced dust fluxes, these pink regions co-located with topographic features such as hills and dunes shown in the inset image here. This provided us with a goal for the present work, which is to simulate the influence of small-scale topography on dust uplift using high-resolution simulations. To this end, we conducted large-eddy simulations of atmospheric winds over a series of topography cases under fairly strong wind conditions, where the surface shear velocity was 0.37 meters per second. The three topography cases are shown here in the animation, with a flat terrain on the top, a smaller hill with 1 kilometer length and 50-meter height in the middle, and a larger hill with the same length and 100-meter height at the bottom. The bottom hill is just large enough for the onset of flow separation, where the mean flow separates from the leeward side of the hill. The domain in this case is periodic, where flow exiting at 2 kilometers enters back at 0 kilometers in x. This effectively simulates a series of hills that the wind encounters. To simplify the problem and isolate the effect of topography on dust uplift, we neglected temperature effects such that this is a neutrally stratified boundary layer, and we also did not include Coriolis forces. To simulate the particle trajectories, we used Lagrangian particle tracking and conducted this for 3 particle sizes, 5 micrometer, 20 micrometer, and almost giant 60 micrometer dust. One of the key limitations of the large-eddy simulations is that it does not resolve the turbulent motions very close to the surface, in between 0 and 1 meter altitude for our case. As a result, we did not include an emission model and instead released the particles 1 meter above the surface at random positions in the XY horizontal plane. As a result, we are specifically studying the fate of particles after suspension and cannot make any conclusions about how topography affects the surface emissions or the very near surface dynamics. After a particle is released, its trajectory is evolved using the equations shown here on the bottom left, where the first equation is a force balance, with this first term being a drag and the second being the gravitational settling. The drag is formulated using Stokes drag, which is corrected here for a finite particle Reynolds number due to the large size of the dust particles. This first equation is used to determine the acceleration of the particle, which then is used to update the position and the velocity of the particle at each time step. In these animations, you can already see the large effect that topography has, at least on the 60 micrometer dust particles. And you can also see the periodicity of the domain, where the particles exiting at 2 kilometers are re-entering at 0. Moving forward into statistics, we are specifically interested in how high all of these trajectories reach by looking at their maximum height relative to the topography, in this case Z prime max. We will be looking at probability distributions due to the large number of simulated particles, where in each case we simulated more than 1 million particles. The plot here shows the probability PR along the horizontal axis that a particle will reach above the altitude Z prime along the vertical axis at any point along its trajectory. For example, if we want to know how likely it is for particles to reach above 100-meter altitude, we can follow 100 meters over to the curve and then downward and see that it intersects around 0.15, indicating there's a 15% probability for a flat terrain with 5 micrometer dust that the particles will exceed 100-meter altitude. Shown here now are all the particle and topography cases in their combinations, and we will specifically be looking at likelihoods that dust is exceeding 200 meters altitude and just use this as a cutoff for considering the dust to be high-reaching. For the 5 micrometer dust particles, there is a factor of 2 to 3 difference in the likelihood that it will reach this height across the different topography cases, indicating that the topography is enhancing transport up to this height by a factor of 2 to 3. If we turn to the larger dust particles in the almost giant size regime, there is an order of magnitude difference in this likelihood, where there's really a negligible probability that the 60 micrometer dust will reach 200 meters with the flat terrain, and this probability becomes non-negligible as you introduce the small-scale topography. Now that we see a significant difference in the likelihoods, we want to look at how these particles are actually reaching high altitudes. And so here we are pre-selecting all the trajectories that at any point exceed 200 meters above the surface, and we will be looking at a distribution of these trajectories. Joint probability distributions are shown here for these high-reaching trajectories, where the darker colored regions indicate a more frequent pathway for the high-reaching dust particles. The plots here again highlight the periodic domain, where we're actually showing 2 instances of the domain and the effect of the particles encountering the hill on 2 different occasions. The distributions for the topography cases indicate 3 possible mechanisms that help to increase the transport of the coarse dust. The first is mean uplift on the windward side of the hill, where dust easily reaches above the height of the hill. The second, specific to the case with flow separation, is ejection away from the hill crest, which you can see by the trajectory of these darker regions, which is in contrast to the smaller hill, which follows the downslope. And the third is dispersion in the highly turbulent wake, where the dispersion helps the particles to reach a wider range of positions. And then as it encounters the next hill, the first mechanism comes into play again, and these particles are reaching even higher altitudes due to the mean uplift. In the next few slides, we'll be looking at each of these mechanisms in detail, starting with the mean uplift. Shown here on the left are the mean vertical flow fields for each of the cases, which is exactly 0 for the flat terrain, and the magnitudes are shown relative to the terminal settling speed of the 60 micrometer particles. Despite being almost giant dust, these uplift magnitudes reach 5 to 10 times the terminal settling speed, meaning that they're more than sufficient to lift the almost giant dust above the hill, as you can see in the animations on the right as it loops through the animation. The mean flow field is asymmetric, such that this uplift is relatively stronger than the leeward downflow. This asymmetry is due to the turbulent stresses on the leeward side of the hill, in addition to the flow separation for the larger hill, which you can see by the separation of these negative velocity contours. This provides us with a segue into the second mechanism, crest ejection due to flow separation. The flow separation is easily apparent from the mean flow streamlines in the left plot, which you can see are separated from the hill over this backflow and recirculation region, and this is in contrast to the smaller hill, which has no such separation. The effect of the separation can be seen in the animation where the particles are initially moving outward away from the hill and lead a deficit in the recirculation region. This effect is seen also in joint probabilities of the trajectories moving away from the hill crest. These trajectories are similar to the previous distributions, except we are not pre-selecting here for the high-reaching particles. And you can see that in the case with flow separation, the particles are more likely to reach positions higher in the wake of the hill relative to the downslope. Once the dust is in the wake, it reaches a wider range of positions due to the third mechanism, dispersion due to turbulence. And the strength of this turbulence can be represented using the standard deviation of the vertical velocity fluctuations, which is the color plot on the left here. Again, the magnitude is relative to the terminal settling of the 60 micrometer particle, and this magnitude is large compared to the terminal settling, indicating that these fluctuations are sufficiently strong to be lifting the almost giant dust particles. And this is apparent in the animation on the right, where you see that the particles released behind the crest are reaching a very wide range of positions, including many of them reaching up above 100 and 200 meters in altitude as they exit the domain. The three mechanisms in the previous slides are not isolated from each other, and indeed they have a compounding effect. In this animation, you can see the particles reaching several hundred meters in altitude through a combination of the mean windward uplift, the ejection behind the crest, and the dispersion in the wake. And you can also see how these effects multiply as the particles reach consecutive hills in the downwind direction. All of these compounding and multiplied effects lead to an order of magnitude difference in the longevity of the trajectories and their ability to reach high altitudes across the different topography cases. However, it is important to point out that we do not expect the topography to entirely explain how coarse dust reaches the Saharan air layer at several kilometers in altitude. We did not simulate these altitudes in our large-eddy simulations shown here. In a typical convective boundary layer, the vertical fluctuations are maximized far from the surface, such that suspended particles in flat terrain are not directly connected to the strongest thermals, and based on our findings have a low likelihood of reaching these heights. In this context, we speculate that the topography mechanism discussed here help to connect the surface dust emissions with the large-scale thermals that then extend to the top of the planetary boundary layer. And this is consistent with the design of the simulations. If you recall, we did not include surface dust emissions in the large-eddy simulations and instead released particles at 1 meter and studied the effect of topography on the fate of those particles. To summarize, we have seen that even gentle topography can create an efficient pathway for coarse and almost giant dust particles to reach several hundred meters in altitude where thermals are present in convective conditions. This pathway includes uplift by the mean windward flow, ejection in the case of flow separation, and dispersion in the turbulent wake of the topography. These mechanisms enhance transport of coarse dust by a factor of 3 for the 5 micrometer sizes and orders of magnitude for the almost giant particles with 60 micrometer diameter. We expect that the systematic underestimate of coarse dust concentrations by global models shown in the introductory slides can at least partially be reduced by considering and parametrizing the effects demonstrated here. To close out, all of the findings from this presentation are reported in a JGR Atmospheres article from earlier this year, shown here at the bottom. And finally, we gratefully acknowledge funding support from the Army Research Office. Thank you for attending.